This presentation will cover concentrated leak erosion, which is a form of scour erosion. Following this presentation, you will be able to identify the internal erosion process of concentrated leak erosion. You'll be able to explain where such leaks may occur, and you'll be able to assess the likelihood of initiating this mechanism. This presentation will provide an overview of the internal erosion process of concentrated leak erosion, and will describe the hydraulic conditions for its initiation. Let's begin with an overview of the internal erosion process. Concentrated leak erosion is a form of scour that refers to an internal erosion process involving leakage flow through an opening in the soil or rock mass. Openings can be cracks, gaps, or other defects in the embankment, or open defects in the soil or rock mass in the foundation. The process is distinguished from other processes of internal erosion by the soil particles eroding from the sides of the opening. This figure shows a continuous defect, a horizontal crack through a homogeneous earth-fill dam. Leakage flow through the crack applies hydraulic shear stresses or tractive forces onto the walls of the crack, and this can lead to particle detachment from the walls of the crack. When an embankment dam is constructed, differential settlements occur across the valley, resulting from parts of the dam being higher than others, settling more as the dam is constructed. This can lead to horizontal strains and potentially cracking or low stress zones susceptible to hydraulic fracture. This is most likely to occur where the abutments are steep, where there is a step in the foundation profile, or where there is compressible soil in part of the foundation. After construction, the embankment continues to settle differentially, resulting in additional stresses and strains. These are inevitable and occur even for well-compacted dams. The figure at the top left illustrates how differential settlements may also result in gaps or cracks opening adjacent to spillway structures. At the bottom, Reclamation's Red Willow Dam experienced cracking over the old creek channel and over the conduit. It has since been upgraded with filters. The cracking over the conduit is a result of the conduit being founded on rock and large differential settlements between the conduit and the embankment in the valley resulting from foundation settlement. The cracking over the old creek section is a result of settlements in the creek section being smaller than in the adjacent embankment. The depth of alluvium beneath the embankment in the creek section was smaller because the rock level was higher here than elsewhere, and the creek was infilled with embankment material. Stepping through the images, you can see how the accumulation of tensile strains increase post-construction settlement as a function of embankment height. Hydraulic fracture involves the formation and extension of an opening in a soil mass due to increasing water pressure. In the figure, an initial opening forms on the upstream side of the core due to a defect or crack. The water pressure in the initial water-filled crack increases, for example due to an increase in reservoir level. If the water pressure in the crack exceeds the sum of the minor principal stress and tensile capacity of the soil at the crack tip, then the crack is jacked open and it extends further into the core. The process progresses from upstream to downstream. Hydraulic fracturing can also occur due to the use of high pressures when drilling with water or air or by pressure grouting. For concentrated leak erosion to initiate, a continuous transverse crack or gap must exist, and the hydraulic shear stresses imposed on the sides of the crack by water flowing through the crack must be greater than the critical shear stress of the soil. The hydraulic shear stresses are dependent on the crack width and the gradient of the flow of water in the crack. The shear stresses are larger for wider cracks and larger gradients. For vertical cracks with a free exit, the highest shear stresses occur at the downstream end of the crack and at the surface of the water flow. The critical shear stress is dependent on the soil classification, clay mineralogy, and the relative compaction and moisture content of the soil. Lastly, there must be sufficient flow velocity through the crack to transport the detached particles. In this typical concentrated leak erosion event tree, Node 1 assesses the likelihood of a transverse crack existing in the embankment. Given the crack exists, Node 2 assesses the likelihood of initiation. These two nodes are the primary focus of this presentation. The remaining nodes will be discussed in separate presentations. Node 3 assesses the likelihood of an unfiltered exit. Nodes 4 and 6 assess the mechanical condition for progression, while Node 5 assesses the hydraulic condition for progression. Nodes 7 and 8 are unsuccessful intervention and breach, respectively. It is good practice to use the generic sequence of events or event tree as a starting point for potential failure mode evaluation, but then to adapt it for site-specific conditions. Not all nodes may apply to a specific dam. In this example, the typical event tree for concentrated leak erosion was adopted to assess the mechanism at the soil-rock interface. Node 1 assesses the likelihood of a continuous open rock defect existing in contact with the embankment. Node 2 was added to assess the effectiveness of any foundation treatment. Given the crack or gap exists, Node 3 assesses the likelihood of initiation. Node 4 assesses the probability of an unfiltered exit. Node 5 assesses the potential for clogging, which could include swelling along the erosion pathway. And Node 6 assesses the mechanical condition for progression. The influence of varying crack widths across the flow path in the foundation on the gradient will be discussed at the end of this presentation. It can affect the hydraulic gradient and potential for clogging. Next, let's cover the situations where concentrated leaks may occur. Where information is available for estimating crack width and depth of a given mechanism, it is included. A broader discussion is provided at the end and in the toolbox overview. This figure shows failure paths that can be associated with structures, foundations, or poor details in the dam. These include locations adjacent to the spillway walls at A and B, adjacent to the outlet conduit at C, and over irregularities in the foundation at D for the upper part of the embankment and at E for the lower part, where low stresses and potential for cracking and hydraulic fracture due to differential settlement are likely. Potential failure paths can also be associated with high permeability layers through any other portion of the embankment. This figure shows some common locations where cracks and defects are often observed. The worst location is usually where two or more factors combine. Understanding the design of the dam, given the geology and seepage history, are key. Searching for potential flaw locations is a very important step in the risk assessment. There are a wide range of mechanisms that can create cracks or other defects through which concentrated leaks can develop. Many of these are related to differential settlement. The initiating mechanism, or IM numbers, correspond to Fell et al. 2024 methodology used in the RMC Concentrated Leak Erosion Cracking Toolbox, which will be covered after this presentation. IM1 and IM9 are for scenarios which may lead to cross-valley differential settlement. IM1 is for cracks in the upper embankment, and IM9 is for cracking in the middle and lower embankment. As a dam is constructed, the partially saturated compacted soil in the embankment consolidates and settlement occurs. Where the valley sides are steep or have steps and benches in the profile, differential settlements occur and can lead to tensile or low stress zones in which cracks may form and hydraulic fracture can occur. This mechanism is more likely for benches and steps in the abutment profile, large normalized post-construction crest settlement, and steep abutment slopes. IM6 is for stage embankment surfaces, which can behave like a step or bench in the abutment profile. Tensile zones develop during the varying stages of embankment construction. This can lead to cracks at depth, but which then close up as additional fill is placed. The following sequence of slides shows the development of minor principal stresses from finite element modeling as an embankment is constructed above a bench in a steep abutment. It should be recognized that these stresses are inevitable, even in well-designed and constructed dams, and are not caused by poor design or construction practice. The following animations progress through the modeling of embankment construction. As fill is placed in layers, tensile zones initially develop above the rock bench and along the steep abutment. These appear as red and orange colored zones. As successive layers are placed, the tensile zones disappear and go back into compression. Therefore, if cracks develop, they are likely to close up as construction proceeds. However, the cracks can remain open or reopen after construction, even at depth due to ongoing settlement. As the fill construction nears the crest, tensile zones develop in the fill adjacent to the steep abutment. The tensile zones in the fill adjacent to the steep abutment remain upon completion of the embankment construction. IM2 and IM22 are for cracking or a gap that may form adjacent to cliffs or walls resulting from the earth fill settling away from the cliff or wall during and after construction. This mechanism is more likely for a vertical or steep cliff or wall close to the sloping part of the abutment profile, a narrow bench between the sloping foundation and the base of the cliff or wall, large normalized post-construction settlement, and a relatively steep abutment slope beneath the core. IM21 is for settlement of the embankment fill resulting in a gap forming at the interface, resulting from wall type and profile between the fill and the upper, steeper part of the spillway or abutment wall. This mechanism is more likely for vertical or steep walls, as shown on the left, and walls overhanging the core, as shown on the right, cantilever walls subjected to cyclic reservoir levels, as well as slender walls with marginal factors of safety against stability, and several concrete buttresses close together or with vertical sides preventing good compaction. IM5 and IM11 are for differential settlement in the foundation resulting in cracking, lateral strains, and low stress zones subject to hydraulic fracture. IM5 is for cracks in the upper embankment, and IM11 is for cracks in the middle and lower embankment. At the top, differential foundation support conditions across the profile include soil and rock. In the middle, a very compressible soil of limited aerial extent is present in the foundation. And at the bottom, differential settlement occurs over the conduit excavation backfill. This mechanism is more likely for deep compressible soil in the foundation, large normalized post-construction crest settlement, and steep foundation interface slopes. IM13 is for cracks in the embankment caused by earthquake. The cracks in embankment dams typically develop near the crest in directions approximately parallel to the dam axis, longitudinal cracks, or transverse to it, transverse cracks. However, cracks are also often observed on the embankment upstream and downstream faces. These figures illustrate some of the mechanisms of cracking often observed in embankment dams after earthquakes. The estimated normalized crest settlement from an earthquake is added to the post-construction crest settlement for cross-valley differential settlement, IM1, and differential foundation settlement, IM5, to assess the likelihood of transverse cracking, crack width, crack depth, and initiation of erosion. Therefore, they are a function of a measure of the earthquake, like PGA, and the water level at the time of the earthquake. Cracks or gaps can also form at embankment interfaces, such as spillway walls. Hydraulic fracturing mechanisms are listed on this slide. Hydraulic fracture is more likely to occur on first filling or during large rises in the reservoir level above the pool of record. It is unlikely to occur under normal operating reservoir levels. IM3 is for cross-valley arching where vertical stresses are shed onto the sides of the valley, which can lead to hydraulic fracture. Factors influencing the likelihood of a continuous transverse crack from hydraulic fracturing are listed on this slide. This mechanism is more likely for very narrow and deep valleys with steep abutments beneath the embankment core. For IM10, vertical stresses in the core of zone embankments can be reduced due to arching between the outer shell zones. This mechanism is more likely for very narrow cores and denser shells, where the Young's modulus of elasticity of the outer shells is much higher than the core. Vertical cores are more susceptible than sloping cores. IM12 is for small-scale irregularities in the foundation of the core, like steps, benches, or depressions in the foundation, that can lead to cracking or low stresses conducive to hydraulic fracture. There are also examples of these irregularities being formed by constructing haul roads across the core and steps in slope correction concrete. For cracking or low stresses to occur, the small-scale irregularities need to be persistent over all or most of the distance across the core. Therefore, narrow cores are more susceptible than wider cores. The steps, benches, or depressions need to be greater than about 5% of the embankment height, and normalized post-construction crest settlement needs to be greater than about 1%. For IM30, arching of the core in the cutoff reduces the total vertical stress in the soil in the cutoff trench. If this is less than the water pressure from the reservoir at that location, hydraulic fracture occurs. Arching action is more likely to occur in narrow and steep trenches, and if the soil in the cutoff trench is not well compacted or is subject to collapse settlement on saturation. Once hydraulic fracture occurs, concentrated leak erosion initiates in the opening formed. For the eroded soil to be transported downstream, the hydraulic fracture must exit into an open defect, such as a vertical joint. Pore compaction mechanisms are listed on this slide. For IM14, a continuous layer of poorly compacted soil in the core may result in the formation of a transverse crack or flaw by the following mechanisms. Mechanism A, the soil behaves as a series of clods with openings between the clods in which water passes. Mechanism B, the soil surrounding a conduit or adjacent to a wall collapses on saturation, forming a gap at the contact of the soil with the conduit or wall, or within the backfilled trench in which the conduit was constructed. Mechanism C, the soil collapses on saturation, causing settlement of the embankment above the poorly compacted layer. The settlement results in arching of the core onto the filters and/or shoulders, resulting in a gap at the top of the saturated soil, most likely at the phreatic surface. Mechanism D, additional settlement of the embankment resulting from collapse settlement in the poorly compacted layer causes transverse cracking. Poorly compacted layers of plastic soils in the embankment core may be subject to settlement on saturation. This is called collapse settlement. Most of the effect will occur on first wetting of the poorly compacted layer, so it will occur on first filling, or in the upper parts of the dam when the reservoir levels equal or exceed the pool of record. However, there is some chance a layer will still experience some further collapse settlement on second and subsequent reservoir levels, which allow water to reach the layer. IM14 is more likely if layers were poorly compacted, with a low relative compaction and compacted dry of optimum moisture content. The poorly compacted layer must persist across the full width of the core. Therefore, narrow cores are more susceptible than wider cores, and this IM is more likely in the upper parts of the embankment. Pore site supervision can be a factor in the likelihood of pore compaction. For IM15, a continuous layer of poorly compacted soil at the core foundation contact may result in the formation of a transverse crack or flaw by the following mechanisms. Mechanism AF, the soil behaves as a series of clods with openings between the clods in which water passes. Mechanism BF, the soil collapses on saturation, causing settlement of the embankment above the poorly compacted layer. If the poorly compacted soil covers only part of the foundation and the soil adjacent is well compacted, differential settlement may result in transverse cracking or low stress zones at the core foundation contact. This mechanism causes localized stresses equivalent to that from a small scale irregularity in the foundation profile for rock foundations, or IM12. Mechanism CF. Additional settlement of the embankment resulting from collapse settlement in the poorly compacted layer causes transverse cracking in the upper part of the embankment. This mechanism is equivalent to transverse cracking in the upper embankment from differential settlement in the soil foundation under the core, or IM5. IM15 is more likely for very irregular rock foundation surfaces with no slope correction, shotcrete or dental concrete treatment, poor foundation preparation beneath the core leading to poor compaction of the first lift of the embankment fill. The poorly compacted layer must persist across the full width of the core. Therefore, narrow cores are more susceptible than wider cores. For IM18, a continuous crack or gap around a conduit through the embankment may result from the mechanisms on the following slides. These scenarios are susceptible to collapse settlement of the poorly compacted fill on saturation and consequently to hydraulic fracture. Mechanism AC is related to poor compaction of the soil around the conduit resulting from the following. In the left and middle, round conduits not being provided with concrete surrounds, making compaction below the conduit difficult or impossible. And on the right, conduits constructed in deep, narrow trenches, which makes compaction difficult, and any settlement results in arching onto the sides of the trench. Poor compaction of the soil around the conduit can also result from conduits constructed in trenches slightly wider than the width of the conduit without enough room provided for heavy compaction equipment. On the left, trench and culvert details for cast in situ or precast rectangular concrete culverts. Good practice is as shown. Poor practice has little or no width between the culvert and slope, near vertical slope, and vertical side slopes for the culvert, which preclude the use of rollers to compact the fill against the culvert. On the right are good details for cast in situ or precast round concrete culverts, showing a rounded top, which is better for localized stresses, and sloping sides to allow compaction with a roller. Poor compaction of the soil around the conduit can also result from the following. On the left, the use of cutoff collars, which make compaction of the soil by compaction equipment, such as rubber tire rollers, difficult or impossible, so backfill compaction is done by hand. On the right, the use of corrugated metal pipe as the conduit, or corrugated metal as formwork for the concrete. The corrugations make good compaction against the pipe difficult. Lastly, a continuous crack or gap around a conduit through the embankment may also result from the following mechanisms. Mechanism BC, cracking of the soils in the sides of the trench in which the conduit is constructed by desiccation and/or stress relief during construction. Mechanism CC, differential settlement of the soil around the conduit, causing low stress zones subject to hydraulic fracture, or IM12. IM18 is more likely for round conduits, not concrete encased, poorly detailed cutoff collars, no formal compaction or poor compaction practices adjacent to the conduit, and inappropriate conduit trench details like a narrow, deep trench with steep slopes. For IM19A, to the left, erosion of the soil surrounding an open defect in a conduit may result in a sinkhole developing above the defect in the conduit. The mechanism for development of the sinkhole depends on the properties of the soil surrounding the conduit. Backward erosion piping of the soil backfill around the conduit is uniform, fine to medium sand, or concentrated leak erosion if the soil is plastic. Depending on the location of the defect, a sinkhole may form below or above the reservoir level. If it forms to exit into the reservoir, the PFM may progress by hydraulic fracture along the exterior of the conduit, resulting in piping failure along the conduit. For IM19B to the right, if a conduit is flowing under pressure, leakage may occur out of cracks or open defects in the conduit. This may result in backward erosion piping of the soil backfill around the conduit downstream of the defect if the soil is uniform fine to medium sand, or hydraulic fracture along the exterior of the conduit, resulting in piping along the conduit downstream of the defect if the soil backfill around the conduit is plastic. If the leakage out of the conduit occurs downstream of the core zone, there would need to be an interconnecting defect through the core zone or for the pipe to head cut upstream to form a continuous concentrated leak through the embankment. If the internal condition of the conduit is not known, this initiating mechanism is more likely for masonry or corrugated metal pipes, poorly detailed joints such as no water stops, settlement of the conduit, and conduit operation, such as a hydraulic conduit with high velocity. See also the RMC Pipe Service Life Flaw Toolbox for factors influencing the likelihood of an open defect in conduits. For IM20, a continuous layer of pore compaction across the core adjacent to a spillway or abutment wall may result in the formation of a transverse crack or gap by the following mechanisms. Mechanism AW. The soil behaves as a series of clods with openings between the clods in which water passes. Mechanism BW. The soil collapses on saturation, causing settlement of the fill. This results in a crack and/or low vertical stress zone within the poorly compacted layer or adjacent to the wall. This mechanism is more likely for no formal compaction or poor compaction practices against the walls, vertical walls with round and irregular surfaces, and several concrete buttresses close together or with vertical sides preventing good compaction. Mechanisms related to climatic conditions are listed on this slide. For IM7, desiccation cracking is a natural process that occurs when soil dries out and cracks form on the surface and throughout the soil layer. Desiccation cracking is seldom present beneath sealed and gravel roads because drying of the core below the pavement is inhibited, or in many cases prevented. Desiccation cracking may also occur on seasonal shutdown or stage construction surfaces, IM8, if good construction practices were not followed, and in soil exposed to drying during construction, particularly if it is compacted very wet. The likelihood of desiccation cracking being present is climate dependent and is most likely to be an issue in arid climates with an average annual net evaporation greater than about 36 inches. The more plastic the soil is, the greater the likelihood of desiccation cracking. The effects of frost are to cause extra water to be drawn into the soil by capillary action. This causes ice lenses to form, with associated heave and potentially cracking. IM16 is for the crest, and IM17 is for the seasonal shutdown or stage construction surfaces, if good construction practices were not followed. This can also occur adjacent to conduits due to freezing and differential movements even if the soil is well compacted. This mechanism is more likely for subarctic or alpine climates where temperatures remain below freezing point for 1 to 3 months. Core materials most susceptible to freezing and ice lens formation include silts, clayey silts, silty sands, silty gravels, and clayey sands and gravels with a PI less than 12. The effects of freezing are more likely with no surface layer or road pavement cover over the core. Other mechanisms shown on this list should be considered where applicable. The following slides will step through the mechanisms. For IM4, a wedge of the core moves upstream because of lack of support from the upstream zones. It occurs when the upstream zones are poorly compacted, such as dumped rock fill. These zones have a low stiffness compared to the core, and the effect is often exacerbated by collapse settlement of the poorly compacted zone on saturation by the reservoir and/or related to major drawdowns of the reservoir. Geological processes which can lead to the formation of open or infill defects or solution features in rock include defects related to the following: stress relief effects in the valley sides, defects related to stress relief effects in the valley floor, such as valley bulge or rebound, solution features for rock subject to solutions such as limestone, dolomite, marble, gypsum, and hydrite and halite, and defects associated with landslides, faults, and shear zones. Blast-induced fractures in abutments and cutoff trench can also lead to the formation of open or infill defects. Inadequate foundation treatment was mentioned earlier in the presentation. At the top right, gaps in the infill material may form by collapse settlement of the infill material upon saturation, incomplete filling of the defect, or hydraulic fracture through the infill. The other erosion diagrams are from the independent panel report on the Teton Dam failure. The figure to the left shows that under high water pressure, the pipe is likely to enlarge by separation of the fill from the rock surface. At the bottom middle, an open joint is not sealed by dental concrete or slush grout. At the bottom right, an open joint at a step in the rock surface is shown, where erosion would occur even more readily because of the reduction of stresses in the reentrant corner due to the arching and poor compaction in the corner. Earth fissures can occur where the ground subsidence causes differential settlements. Possible causes include groundwater extraction, oil extraction, and underground mining. Earth fissures can be along the edges of the subsidence area, or as shown in the figures, where the thickness of the soil deposit varies. Animal burrows can lead to situations where there are nearly continuous holes through an embankment, or situations where high gradients between holes may result in initiation of concentrated leak erosion. In the photos, large rodent burrows associated with assumed beaver activity at Natomas Levee were observed by operation and maintenance personnel. A beaver was actually observed carrying a large tree branch towards the levee, disappearing at the toe, and then reappearing on the opposite levee toe, still carrying a branch. Upon walking down the levee slope, personnel found a large entrance hole. An investigation was undertaken to investigate the size, magnitude, and continuity of the beaver den network. The network penetrated through much of the embankment. Vegetation growing on embankments can lead to situations which may lead to concentrated leak erosion. Decaying roots or roots penetrating into an open joint and cracks in the foundation rock can create seepage paths. Overturned trees can create shortened seepage paths. Root penetration of conduit joints and joints in other concrete structures can open the joints to allow erosion into or out of the conduit or wall. Roots can also clog underdrain systems, and vegetation in general can hinder visual inspection. The hole in the photo at the top right was created on the waterside levee slope by a rotted tree stump. The photo on the bottom right is of a breach due to overtopping, but it exposed large roots that penetrated the embankment. Crack width and depth. Crack width for vertical cracks resulting from differential settlement are a function of localized tensile strain. The higher the tensile strain, the larger the crack width. Case histories of crack width and crack depth to crack width ratio are shown in the figure. Fell et al. 2024 provided the relationship shown. This table provides widths of cracking and hydraulic fracture resulting from arching. For IM3 and IM10, these widths apply for all reservoir stages. For IM12, these widths should be considered applicable to reservoir stages where the increase in reservoir pressure is 2,000 psf or more above pool of record level. For increases in reservoir pressure from 0 to 2,000 psf, the crack width should be scaled according to the pressure increases. These widths are approximate and are given only as a guide. The most likely location for cracking and hydraulic fracture resulting from arching are summarized on the slide. For IM3, see section S5.4 in the supporting document for two examples of numerical modeling showing where hydraulic fracture is likely to occur. In the absence of other information, assume hydraulic fracture may occur at all levels within the core. For important decisions, carry out dam-specific numerical analyses. For IM10, the most likely location for arching to occur is in the upper middle embankment. Core material susceptible to collapse settlement may result in arching and low stresses. Collapse settlement may also lead to softened zones and a crack in the vicinity of the contact between the saturated and unsaturated parts of the core, for example at the phreatic surface. For IM12, hydraulic fracture may occur in low stress zones over irregularities in the foundation profile. For IM30, the hydraulic fracture in the cutoff trench must coincide with an open defect in the foundation at the downstream core foundation contact to provide an unfiltered exit. Coincidence is more likely for vertical defects than for horizontal defects. This table provides guidance for effective opening gap size between soil clods as a function of method and degree of compaction of the embankment core. This table provides guidance for normalized collapse settlement, which may occur on saturation as a function of degree of compaction. These are for first filling and reservoir levels above pool of record. There may be a single poorly compacted layer or several layers. The minimum poorly compacted layer thickness adopted should be 12 inches. Using the normalized collapse settlement from the previous slide for first filling and reservoir levels above pool of record, the amount of collapse settlement can be estimated using the guidance on this slide. Tables for estimating crack width and depth resulting from desiccation are based on case histories. The higher the liquid limit, the wider and deeper the desiccation crack. The conditions on the crest also play a role, with thicker gravel roads limiting the crack size. Desiccation cracking is not expected beneath seal roads or concrete pavements. Suggested crack widths as a function of the likelihood of transverse cracking due to freezing are provided on the left, and suggested crack depths as a function of climate are provided on the right. However, the most reliable source for depth of frost penetration is the local building code, or structural load data tool for UFC 3-301-01 for Department of Defense locations from the Whole Building Design Guide. Initial estimates of crack depths can be made using analytical methods, but case histories can provide some ground truth of what has actually happened. The table on the left summarizes the results of maximum depth of transverse cracking in dams worldwide performed by Virginia Tech for reclamation. The table on the right summarizes the cracking observed in dams and some of the factors which influence whether cracking may occur. Next, let's cover swelling potential. The general principles for the assessment of whether a crack or flaw will close resulting from swell of the soil in the sides of the crack or flaw are shown on this slide. The amount of swell depends on the swell properties of the soil, the degree of compaction, and the moisture content relative to the standard Proctor optimum moisture content, and whether the soil is at as compacted moisture content or has dried since compaction. Whether a crack closes or remains open depends on the initial crack width, the amount and rate of swell, and the rate of erosion and crack widening. Guiding principles for estimating probabilities by expert elicitation are shown on this slide. Soil swell effects are likely to be more critical where the predicted crack widths are narrow, such as 2 to 5 millimeters. Based on the estimated crack width, any laboratory swell tests, and the soil's properties described on the previous slide, estimate the probability that the crack will close by swelling. Teams may need to add an inventory node for does the crack close by swell of the soil in the sides of the crack. The figure on the left shows a classification chart for swelling potential as a function of soil activity and clay fraction, which is the percentage finer than 0.02 millimeters. The figure on the right shows the time for an open pipe to erode from 1 millimeter to 5 millimeters in diameter as a function of the whole erosion rate index for the embankment core material and hydraulic gradient within the pipe. This figure can be used as a guide to assess whether there is sufficient time for a crack to swell shut prior to erosion progressing back from the downstream end of the crack, where hydraulic shear stresses are the highest. Toolbox overview. The RMC Concentrated Leak Erosion Cracking Toolbox provides resources and methods to estimate the probability of continuous transverse crack from the various mechanisms, crack width, and crack depth or location. It also contains guidance on estimating swelling potential and some limited case history data for crack width and depth. The hydraulic condition for initiation requires an estimate of the crack location and geometry, the applied hydraulic shear stress in the pipe or crack, and the critical shear stress. Concentrated leak erosion will initiate when the applied hydraulic shear stress exceeds a critical value as described in Node 2 of the typical event tree. This requires estimating the hydraulic shear stresses in the crack for the water level under consideration, taking into account the geometry of the core and assumed crack dimensions and location relative to the water level so the flow gradient can be determined. A simplified crack geometry is usually assumed, which may result in very conservative estimates. As such, sensitivity analysis is strongly suggested. When assessing initiation, potential head losses in the zones upstream and downstream in zone dams may need to be considered when estimating the gradients in the crack. Once the hydraulic shear stress has been estimated, it is compared to the critical shear stress, which will initiate erosion for the soil in the core at the degree of saturation of the soil on the sides of the crack. These figures provide examples of transverse flaws, pipes or cracks, for which the hydraulic shear stress will be estimated. The geometries include a cylindrical pipe, a horizontal crack, a vertical rectangular crack, and vertical tapered crack. The equation for estimating the hydraulic shear stress in cylindrical pipes and horizontal cracks through the core is shown on this slide and is equal to the product of the unit weight of water, the hydraulic gradient of flow in the pipe or crack, and the ratio of the cross-sectional area of the crack to its wetted perimeter. The pipe or flaw is assumed to have a uniform cross-section, and head loss is assumed to be linear. Uniform frictional resistance is also assumed along the surface of the flaw. For the case of tailwater below the base of a cylindrical pipe or horizontal crack, the hydraulic gradient across the core is estimated by dividing the hydraulic head difference by the length of the leakage pathway through the core. A homogeneous cohesive embankment is shown on the left, and the slope of the upstream and downstream faces are used to estimate the length. A zoned embankment is shown on the right, where the upstream and downstream zones are very permeable, for example, rockfill. The slopes of the upstream and downstream central core are used to estimate the length. To calculate the hydraulic shear stress in a pipe or crack, Wan 2006 developed equations for cylindrical pipes and vertical rectangular cracks with no tailwater. The Corps of Engineers expanded these equations to include tailwater and developed equations for horizontal cracks. If you do not have access to toolbox analysis, you can use these simple equations in the last column to obtain a decent estimate. Another way to use the hydraulic shear stress relationships is to assess the critical pipe diameter or crack width for initiation of concentrated leak erosion. Once the critical diameter or width is estimated, the risk assessment team can then consider the likelihood of having a pipe or crack of those dimensions. An estimate of critical shear stress is still needed, and a range of values should be considered. Scour can also occur along continuous open rock defects in the foundation. The method for assessing the likelihood of initiation of concentrated leak erosion is just like for pipes or cracks in the embankment. The hydraulic gradient may vary across the flow path in the foundation as the width of the open defects varies, as shown in the series of figures on the right. Erosion will initiate in the narrow defects where gradients are high in preference to the wider sections of defect. Recent numerical modeling and laboratory testing by Pearson et al. At the University of New South Wales showed that the flow is controlled by the exit conditions at the downstream end of the crack. Hydraulic shear stresses are highest at the downstream end and much lower at the upstream end. The highest stresses occur at the surface of the water profile. As erosion occurs, the downstream end of the crack widens and the water surface in that part of the crack lowers. The new control becomes the non-eroded crack just upstream of the eroded part. This process will progress upstream and not cease unless the crack closes by swell at the upstream end, filters arrest erosion, or there is a drop in headwater. In this figure, Z30 is the water level at the upstream end of the crack for a 30-meter reference crack length, and Z0 is the water depth at the downstream end of the crack. The crack width, depth, and side slope in the figure are summarized in the blue text box. A numerical model was used to develop charts to estimate the peak hydraulic wall stresses based on representative embankment crack geometries. The top charts are for vertical rectangular cracks, and the bottom charts are for vertical triangular cracks. After the water level at the downstream end of the crack converges, the hydraulic shear stresses can be evaluated. The figures on the left are for the maximum hydraulic shear stress at the downstream end of the crack, and the figures on the right are for the profile of the maximum hydraulic shear stress along the length of the crack. The top figures are for vertical rectangular cracks, and the bottom figures are for vertical triangular cracks. And finally, the total steady flow through the crack can be obtained. The figure on the left is for vertical rectangular cracks, and the figure on the right is for vertical triangular cracks. In lieu of the simplified graphical method, the following table can be used to estimate hydraulic shear stresses for open vertical cracks with a free exit. The simplified graphical method and previous table assume that there is a free exit for flow at the downstream face of the crack. The flow is hydraulically controlled at the downstream end by the crack dimensions. If there is a filter, transition, or rockfill zone downstream of the cracked core, there may be additional control on the exit conditions, resulting in a change in the flow profile in the crack and a reduction in the hydraulic shear stresses compared to the free exit conditions. See pages 125 to 127 in Fell et al. 2024 guidance document for some suggested guidance. More and less likely factors for the geometric conditions. Factors increasing the likelihood of a continuous transverse crack or gap were provided for each initiating mechanism on the previous slides. Case studies provide insights into conditions in which cracks have been observed in embankment dams. Most dams settle less than 0.5% in the 10 years after construction, as illustrated by these two figures, which is less than those in which cracking has mostly been observed. Starting with the plot on the left, many dams with cracking experience 1% to 2% post-construction settlement as a percentage of the maximum embankment height. However, cracking was also observed where post-construction settlements were significantly smaller, but other unfavorable conditions generally existed. A similar plot of post-construction settlements was performed for 20 Corps of Engineers Louisville District dams. J. Edward Rauch Dam experienced settlement adjacent to a spillway wall, and Mississinawa Dam experienced settlement due to internal migration of the embankment into the foundation. Numerical analyses show that for differential settlement, strains tend to localize. So it is important to be able to predict what localized strains are likely to result in cracking. To get a feel for the maximum localized strains which might have occurred in case histories of dams with cracking, parametric models, which most closely represent the valley profile of the case histories, and the post-construction settlement were used to estimate the localized strains and accumulated strains at the crest. Most cases of cracking had estimated localized strains greater than 1%, and many about 2%. The probability of transverse cracking is estimated by first estimating localized strains as a function of the post-construction settlement and the valley geometry. The potential width and depth of cracking are estimated from the localized strains. For important decisions on dam safety and upgrades, these should be estimated by cross-valley numerical and crack propagation analyses. This table from McCook and Gortry in 2009 can be used to help assess the likelihood of hydraulic fracture. Finite element programs like GeoStudio Sigma W can also help assess the potential for hydraulic fracture in the embankment for new construction. By comparing the predicted lateral stresses to predicted reservoir pressures, the likelihood of hydraulic fracture on first filling of the reservoir can be assessed. The effects of various design parameters, such as degree of compaction, placement water content, removal of foundations, shaping of transverse slopes, and other factors can also be assessed. This table from the Best Practices Manual can be used to help assess the likelihood of initiation of concentrated leak erosion. It can be used as a starting point, but the risk team must develop project-specific more likely and less likely factors to guide subjective probability estimation. The factors in this portion of the table address seepage, soil erodibility, cracking, sinkholes or depressions, and loose or soft zones in the core. The factors in this portion of the table address construction practices, core width, differential settlement of the foundation, and foundation profile under the core. The factors in this portion of the table address observed settlement, foundation preparation, and abutment slopes. The factors in this portion of the table address differential settlement due to a closure section, seasonal shutdown layers, embankment zoning and overall geometry, and the quality of construction and quality control. The factors in this portion of the table address lift thickness, core materials, desiccation, cracking, and instrumentation. And the factors in this portion of the table address reservoir operation, vegetation, and age of the dam. Toolbox overview. The RMC Concentrated Leak Erosion Initiation Toolbox calculates the hydraulic shear stress in a pipe or crack and compares it to the critical shear stress of the soil. Multiple crack geometries can be assessed. For parameter combinations where the stress exceeds the critical shear stress, initiation is assumed to occur. The toolbox will also calculate the critical pipe diameter or crack width for a given critical shear stress and hydraulic loading. Since the development of Fell et al. 2008, the understanding of the mechanics of internal erosion has improved, and significant experience using the piping toolbox has been gained. As a result, the 2008 document is out of date. The worksheets involving vertical, rectangular, and tapered cracks and the average gradient method should no longer be used. An update to the RMC Concentrated Leak Erosion Initiation Toolbox is being developed for open vertical, rectangular, and triangular cracks. The primary references used to develop this presentation are listed on the following slides. This concludes the presentation on concentrated leak erosion.